In this module, we can discuss the basic concept of M-ary transmission techniques. So before going to the M-ary transmission techniques, first let us see, we have discussed three types of different keying techniques, namely amplitude, frequency, and phase shift keying. Out of these three techniques, we know that the phase shift keying has lot of advantages compared to ASK and FSK. Because in ASK, we know that we have amplitude variations. So because of amplitude variations and low Euclidean distance, the probability of error is more in the case of ASK. In FSK, even though there are no amplitude variations, but here the bandwidth requirement is more in FSK, which is equal to 4 times that of FP. In PSK, we have no amplitude variations. Similarly, the Euclidean distance is also very high, and it is equal to 2 root ES. Once the Euclidean distance is more, automatically the probability of error will be less, which leads to the improvement in the SNR. So PSK has a lot of advantages when compared to ASK and FSK. It has a high noise immunity, similarly less probability of error due to its high Euclidean distance. Similarly, the bandwidth utilization, in order to overcome the bandwidth utilization of PSK, having the bandwidth of 2 FP. In the binary PSK, the bandwidth is 2 times that of FP. But in order to overcome this problem, in QPSK, if you merge, in QPSK, we have seen that if you merge 2 bits per symbol, then its bandwidth is reduced to FP. So if you, as and when if you group a more number of bits per symbol, automatically we are going to reduce the bandwidth requirement. So that's why, because PSK has a lot of advantages like high SNR and high noise immunity, less probability of error, and no amplitude variations, we can prefer PSK. And when compared to BPSK, QPSK has a less bandwidth, and at the same time you are transmitting 2 bits at a time, that you are grouping 2 bits per second. That's why it is symbol, it is called as depict. Similarly, a PSK system having 8 phase changes is called as 8-array PSK, where 3 bits are grouped per symbol. So bandwidth will be 2FP by N. So 2FP by 3 is the bandwidth of 8-array PSK. So M-ary PSK has M number of phase changes whose bandwidth is 2FP by N, where N number of bits are grouped per symbol. So in M-ary PSK, we can reduce the bandwidth. At the same time, it has same advantages as that of PSK. That's why these are all the advantages of M-ary techniques, and out of that we are mainly focusing on M-ary PSK because of having more number of advantages for PSK. Now coming to the M-ary transmitter, here initially B of t is a bipolar signal. We know that it has 2 amplitudes plus or minus 1. The same we discussed in the earlier modules. In PSK, especially in BPSK and QPSK, we discussed the bipolar energy, and that bipolar energy B of t, our input data, it is initially converted into a parallel data. So that series data is converted to parallel data. So at a time you are sending n number of bits. So here you are grouping n number of bits. So that n number of bits, where capital M is represented as 2 power n. So you will have m number of phase changes. That's why it is called as M-ary PSK. So you are grouping a small n number of bits that range from 0 to n minus 1, where m is the number of phase changes. And that data is converted into analog format. So let us suppose the analog version of the digital NP group data be M of t, and this M of t is now applied to a phase modulator. For example, if it is FSK, you will apply this to frequency modulator. Because this is M-ary PSK, a phase modulator is used here for analog signal transmission. So finally, an M-ary PSK signal is received. that signal will be sent to the channel. So here we mentioned that, yeah, in here you will have m phase changes of the carrier to transmit the data, where m is equal to 2 power n, where n is the number of bits grouped per symbol. Here remember that all the m possible waveforms have same amplitude and frequency but different phases. So here if you see, an M-ary PSK signal is defined as root 2ps into cos omega ct plus phi m, where phi m is a phase change which is defined as 2m plus 1 into pi by capital M, where capital M is the number of symbols which is equal to 2 power n, where small m is a variable that range from 0 to capital M. That is where capital M represents the number of phase changes which is equal to 2 power m. So phi m is equal to 2m plus 1 into pi by m. For example, let us see. And the phase difference between the two successive symbols is 2 pi by capital M. For example, let us take QPSK, where capital M is equal to 4. So small m will be 0, 1, 2, 3. So 4 combinations will be there. So let us substitute 0, 1, 2, 3 values of m respectively to evaluate the phase change. So phi naught is equal to 2 into 0 plus 1 into whole into pi by 4. Similarly, phi 1 is 2 plus 1 into pi by 4. So phi naught, phi 1, that is 3 pi by 4. Phi naught is pi by 4. Phi 1 is 3 pi by 4. Phi 2 is 5 pi by 4. And phi 3 is 7 pi by 4. So you have total of 4 phase changes because it is a QPSK. Similarly, for M-ary PSK, you will have capital M number of phase changes. Let us see the constellation diagram of 8-array PSK, where you will have 8 phase changes. So if you observe the figure, here you can see that there are 8 phase changes. And each has a phase shift of pi by 4. Similarly, if you extend the same to M-ary PSK, that is 2 pi by m, you will have total of m, capital M phase changes with a phase shift of 2 pi by m. Similarly, the Euclidean distance between the two symbols, for example, here these are the two symbols Sm and S1 and Sm, capital M minus 1, or between S1 and S2, or between S2 and S3. If you observe, the Euclidean distance is defined as 2 root PSTS into sine pi by m. Because if you let us evaluate the Euclidean distance, let us consider the distance between the 2 points B, D12, where D12 is a Euclidean distance. So from the figure, if you see, sine pi by m is equal to D12 by 2, because we are taking only the distance between AB. So AB by OA. So it will be D12 by 2 divided by the distance between O and A. It is root ES. So that's why 2 root ES sine pi by m is the Euclidean distance for M-ary PSK. Let us replace m as 2 for BPSK. Then 2 root PSTS into sine pi by 2, because m is 2 here. Then it is 2 root PS into TP. The same we evaluated in the BPSK. This we already discussed in the BPSK module, that is in the earlier lecture. For example, for QPSK, M will be 4, so TS will be 2 TB. Let us replace TS as 2 TB and replace M as 4. Then it is 2 root 2 into PS into TB into 1 by root 2. Then D12 will be 2 root PS TB. Similarly, the bandwidth of M-ary PSK is 2fs. So that is 2 by Ts, where Ts is n into TB. So 2fp by n is the bandwidth of M-ary PSK. This is the general expression. Even in the figure also you can see that the bandwidth is upper cutoff, that is fc plus fs minus fc minus fs. So then our fc gets cancelled, so you will get 2fs. Upon substitution as of Ts as n dB, you will get the bandwidth as 2fp by n. Let us go through the M-ary PSK receiver. So this you can see, if you see this block diagram, this is similar to the block diagram of M-ary binary PSK, but instead of square law device, here you have raised input to the power of m. And similarly, in BPSK, you have band pass filter of cutoff 2 FC, but here the band pass filter cutoff is m into f naught, because it is for m number of phase changes or n number of bits are grouped per symbol. Similarly, here you will use a frequency divider by m. These three blocks we already discussed in the earlier lecture that these three blocks are required to generate the coherent carrier. Here cos 2 pi f naught t is the coherent carrier, which is multiplied with the received M-ary PSK signal to produce the output as S of t into cos 2 pi f naught t, where S of t is the M-ary PSK. Now that is applied to the integral, which takes the even intervals. Then you will get Ts into Pe as the output of correlator 1. And similarly, in the correlator 2, you have a multiplier that multiplies the upcoming M-ary PSK signal with sine 2 pi f naught t. Then our output is a correlated, then the output is applied to the integrator, where the output of multiplier 2 in correlator 2 is S of t into sine 2 pi f naught t. So the output of correlator 2 is Ts into P naught. Now our these two outputs are from correlator 1 and correlator 2 are applied to the A to D converter, because till now we are doing the analog transmission, and that is converted to digital. And the digital data, which is a parallel data, is converted into because we have grouped n bits per symbol. Now that is converted into a series sequence, which is a demodulated output, which is proportional to the message signal. So in this module, we have discussed the concept of M-ary techniques, and we have extended the same to M-ary PSK. And we discussed M-ary PSK transmitter and receiver and some of the features of M-ary techniques. And if here you can see the advantages of M-ary PSK. Here it is completely bandwidth and power efficient over binary transmission techniques, because here bandwidth is only 2FP by N. The bandwidth of M-ary PSK is 2FP by N. M-ary PSK is highly noise immune because it is a PSK technique having no amplitude variations and high Euclidean distance. So its probability of error is low. That's why the information rate is high, and similarly probability error is less. These are all the advantages of M-ary PSK, and here the applications are similar to the binary PSK and quadrature PSK, and somewhat it's also extended to all mobile communications. And similarly, optical communication, these are all the applications of PSK. Along with the PSK applications, it is also applicable to like the applications that include space data, similarly satellite communication. So there are a lot of advantages for M-ary PSK and used in varieties of applications as mentioned here. So in this module, we have discussed the M-ary transmission techniques. In the next module, we can discuss the comparison of all the shift keying techniques. Thank you for listening.